Hi, I'm going to be talking about my work for analysis of models for decentralized and collaborative AI on blockchain. We also call this project Sharing Updatable Models, or SUM, on Blockchain. I'm presenting this for ICBC 2020. I'm Justin Harris. I'm a senior software developer at Microsoft, working with people in Montreal, but right now I'm working out of Toronto. I'll give an explanation of the project. I'll talk about the motivations for this work, some of the machine learning models that we experimented with, and the data sets that we experimented on for this work, and then I'll talk about some of the results of those actual experiments. So this talk is an update to a project that I've been working on for a while, so I'm going to kind of go over quickly some of the initial work, and then I'll talk more details about the actual updates to this project. So kind of the motivations for the original work is that working on machine learning models is difficult because there's a lot of things that you have to worry about: deploying those models, scaling them, keeping them up to date and training them, and then getting people to actually write those models. So we want to solve some of those things by putting machine learning models in smart contracts on a blockchain. And by putting these models, actually the weights for these models, and putting them in smart contracts, you can get people to update these models and incentivize them by giving them rewards for their data if they've given good data. So I'll talk about some of the ways that we do that. So some more specific motivations here is: imagine that you can actually improve models live with real world data while they're deployed. So you can think about this sort of as a live, ongoing crowdsourcing process. And putting models in smart contracts gives you access to more data and more people, and there's no central authority for these models compared to typical machine learning systems. So lots of people can give their data to these models and no one owns them, and different companies can share them. So imagine, like, for a fitness tracker, that Garmin and Fitbit can share the same underlying model to predict what activity people were doing when they see certain data. Or imagine for detecting fake news, that different media organizations can share the same underlying detection model. So how would this actually work? Well, you would have someone come along and they would deploy an initial model to a smart contract. People can come along and give their data, and they'd be required to give a deposit of some funds along with their data they give. So this is typical in a blockchain system where people are kind of staking a deposit for something, and if we determine that their data is good, they can get their deposit back and maybe even a reward. I'll talk about some ways that we validate this data later. And the model remains open to the public to use for free, of course, because it's in a smart contract and anybody can just read the data off of that smart contract and use the model. So adding data consists of 3 steps. The data with features X and label Y is submitted to an incentive mechanism, which would validate, say, that the deposit is enough when this data is given. If it's valid, we submit the data to a data handler to store it in the smart contract, and then we actually update the model. And this is all done within smart contracts. So then the model is able to be used for free, and people can call prediction on it. Just to kind of go over some assumptions here, we're assuming that a blockchain is basically public and global and immutable. I'm talking about public chains here. Of course, if you want to do things on private chains, you're way less limited. I'm talking more about public chains. And in particular, we did experiments with Ethereum. So you have this Ethereum public chain network all over the world with nodes running all over the world and these smart contracts available. So the reason we're doing this on a blockchain is to take advantage of some attributes that a lot of different smart contracts want to take advantage of, in particular this publicness, persistence, and decentralized nature. What's also happening here is transparent compared to a typical crowdsourcing system. You might not believe that you'll actually get paid for the data that you submit to it. So this transparency and trust is important, that you can be sure the model is actually going to get improved, and you can hope that you actually get your funds back. So this initial work gained some popularity. I presented at the second IEEE conference on blockchain last year. We're building off some other work. You might have seen other stuff about paying to use models and that being facilitated using a blockchain and kind of marketplaces for data. That's a little different. There's also work on running Kaggle-like experiments, Kaggle-like competitions on Ethereum. But in those cases, the models were not updatable. Here, you can actually train the models in the smart contract. There's been other proposals for crowdsourcing on blockchains, and other interesting work related to AI and blockchain. So the models that we're talking about here, they're supervised models with features X and labels Y. And one of the goals here is that we want to minimize the gas costs, because training models in smart contracts can actually be very expensive. But we're going to just talk about a few simple models here, like naive Bayes, your centroid classifier, and a perceptron model. So just because we're using simple models in the smart contracts doesn't mean that we can only do simple applications. You can have some very complicated models where, here, you can have some very complicated models, say where these initial layers or encoders are fixed and done off-chain, and then this more complicated classifier part exists in a smart contract. So you can think about this as like a fine-tuning process where you're fine-tuning this final classifier on-chain and the rest is done off-chain, and people kind of understand and have a standard way of doing this, but they want to update this final top part of the model. So the models that I'll be talking about can all be updated very efficiently. We'll start by talking about the naive Bayes classifier. So you have some features X, the classification or label C, and basically to update this, essentially what it all comes down to is keeping track of a bunch of counts of the number of times you've seen each feature within a class and the total count of all the features in that class. What's nice here is that it can support multiple classes. A nearest centroid classifier, so this you can just do a moving average to update the values in your centroid. So how does this classifier work? Imagine you have a bunch of blue squares here of one class and red triangles of another class, and you get a new point. You want to see which class it could be, so you compute the average for each class of the centroid. You see which one's closer. Here in this case it's closer to the red triangle, so we would label it as such. This one's interesting because you can do an encoding off-chain like I talked about before, and then use this as a classifier for fine-tuning, and you can even do that with 512 dimensions, and it can be done in one transaction in Ethereum. It will not go over gas costs. A perceptron model, this is very typical machine learning, and what's nice here is, again, the update is very efficient. You just have to update some weights for the number of features that you have. And what can be very efficient here is that you don't update the model if it already agrees with the classification. So if the predicted class is equal to the expected class, you do not update the model. So I'm going to talk about how this would actually look in the real world. And for this research, I'm mainly talking about the incentive mechanism that we call the self-assessment incentive mechanism, where people would deposit some funds to get data, and they can request a refund for their deposit if their data is good, and they can take deposits from others if those other people submitted that data. So let's look at a demo. Suppose you had some dashboard that somebody created where they list off a bunch of models that are in smart contracts, and you can do this because we're assuming things are on a public blockchain where they can be examined for free. So there's a few different models we can dive into. Let's say we want to improve this IMDb review sentiment analysis dataset. So they try it out. Let's say they wrote a movie review. They say great movie. The model predicts that this movie review is positive. That's correct. So they try out the model a bit. They think it works well, but maybe they find a bug. They can train this model and update it. So they say this was the best movie ever, and that should have a positive sentiment. So they click on train. MetaMask pops up and asks would they like to confirm this transaction. So the deposit here is proportional to 1 over the time since data was last added. So with this incentive mechanism, that's a way to stop people from submitting lots of bad data in a short amount of time. It would make that very expensive. So they click confirm, and we can now go to the refund step. So if after some time we validate their data as good, then they can get a refund for that. So the way with this incentive mechanism, we're assuming data is good, is if after some time the model agrees with that label that they provided. So of course there's bias problems here, but this is just the initial idea. So it's kind of like a Wikipedia type system where after some time, let's say a week, if the model still agrees with the classification that they provided, we're going to assume that nobody corrected it. It's kind of similar to how in a popular Wikipedia article, you can assume that the data and the information in there is mostly correct, otherwise somebody would have changed it or flagged it or something like that. So for better or worse, that's just what we're assuming now is this initial proposal. Future work is of course encouraged. And if somebody submitted bad data, well, hopefully that somebody else corrected it or the model just didn't agree. Otherwise, this person can submit more data to help correct the model. But if after some time the model doesn't agree, they will not be able to get their deposit back. People that have added good data earn points, and they can take the deposit from those that have added bad. So just in summary, people submit data along with a deposit to stake that this data is good. People can get a reward along with people can get a reward if their data is determined to be good, and the model remains open to use for prediction for free. So I ran experiments using several different data sets, and all of these are scenarios where people would benefit greatly from collaborating across different platforms. So for fake news detection, trying to detect if a news article is reliable or not based on the language used in it, and this is a data set available on Kaggle. The FitRec activity prediction data set, so this was published by Endomondo, and you have various attributes of people doing various activities from their fitness tracker, and we're gonna try to predict if people were biking or running. And the popular IMDb movie review data set, where we want to predict if the movie review was positive or negative based on the text used in that. And that's more interesting not just for movie reviews, but more so for to detect online bullying or something like that, to detect the sentiment of a post or comment that someone might make in a social network. So I ran simulations for each of the models I talked about earlier with respect to comparing how they did on each of these data sets. So in these simulations, each sample from the data set was submitted to the model once. We're going to just assume that there's two agents, one representing all the good people and one representing all the bad people. We're going to monitor the accuracy with respect to some hidden test set that we left out of the data set and did not train with. And we're going to measure the agent's balance to make sure that good people don't lose all their money, see the model's accuracy. It's important that the model can remain accurate, and then check Ethereum gas cost to make sure it's not crazy expensive to participate in the system. All the code is public, so there's Python code for the simulations and Solidity and JavaScript code for the Ethereum gas cost checks. So some of the different assumptions that we made here, we're going to assume that the bad people are willing to spend more to corrupt the model. They might represent a competitor, say, that would want to ruin this system and this model that people are depending on. And we assume that the good people who are submitting correct data, well, usually they submit correct data. They might make a mistake and accidentally give incorrect data. And we're going to assume that they can see some accuracy on that hidden test set. Now, maybe in a real world, they don't actually all see the same number, because they might have different test sets that they created themselves. They might pay for access to some accuracy on a hidden test set or something like that. Okay, so for the first one, the fake news detection data set. So here, the pattern is that the naive Bayes model is always with the solid line, the nearest centroid classifier with the dashed line, and then the perceptron using the dotted line. So with each model, the agent representing the good and honest person was able to profit, and the bad agent lost all their funds. And the perceptron has the highest accuracy. But what's interesting is the naive Bayes was able to pass this kind of baseline accuracy that we've built. So these numbers that you see here, this is as if you trained with all of the data in the training set. And it's kind of hard to see in this one, but you'll see in others. So this kind of bluish solid line is from the naive Bayes, its accuracy changing over time. So I'll talk a bit about the features for this data set. So the features for this model was, there's 1,000 features for the term frequency of the top 1,000 bigrams in the training set. So when we just checking gas costs, we're going to look at data samples that had 15 integers, and these are representing the occurrence of 15 bigrams that occur in those top 1,000 bigrams from the training set. So looking at these gas costs, the perceptron, and this is a trend you're going to see throughout them, is usually the cheapest to use, and that's because for these other multi-class classifiers, they have to keep data for each class that they support. Like the naive Bayes has to keep track of all those counts for each class. The nearest centroid has to keep track of averages for each class that it supports. So deployment cost is going to be almost twice, because there's essentially twice the information compared to the linear perceptron. The predict function is not listed here, and that's because predict is something we don't really need to measure directly on its own, because it can be done off-chain. Remember, the whole smart contract is public, so we don't really need to worry about gas costs, but that predict function is done in reward and refund, because you need to run that prediction before you can decide if you should refund or reward the reporter. The update for the sparse nearest centroid, that can actually be done very efficiently without updating all of the averages, because it came up with a little something to essentially store the denominator for each value in that centroid, and so we only update the values that we need to, that's part of this data. So in this case 15 numbers, and we're keeping track of the denominator, so at prediction time we can either use that denominator if it's correct, or compute the correct value for that centroid. Sorry, I'm kind of being vague here. All the code's public, you can feel free to look at it. Next is the activity prediction data set. So here we want to detect and predict, if someone is biking or running based on a few features. So these are all discretized so that we can use them for the naive Bayes classifier. Each classifier gets the same features, of course. So we're looking at heart rate, the maximum speed, the minimum speed, average speed, median speed, and the gender of the person. So what's consistent here is that the honest, good agent is able to profit, the bad agent loses a lot of their funds. Most of the models can maintain their accuracy, but the perceptron here, that's this one that's dipping. So that one, eventually it corrects itself and comes back, but it is not able to maintain the accuracy the whole time, and that's likely because for this perceptron, it only updates if it disagrees with the provided class. So the malicious contributor, this bad contributor, is able to change it a lot because it's contributing data it disagrees with, but when the good people add data, they're able to counteract that and bring it back closer to that baseline, basically ideal accuracy. So again, like before, the perceptron is usually the cheapest, with the naive Bayes actually coming close here, and that's most likely because there's so few features here. If we were to do something, have a lot more features, which I've done other experiments with, you would see these costs being very high, especially for this dense nearest centroid classifier. The IMDb movie review one, so this is another text one, like the fake news one. Here we want to predict if the movie review is positive or negative. Again, there's 1,000 features, but this is a little different because these are just word features. Before, with the fake news, it was bigram features. So most models are able to maintain their accuracy. Here's this as a simulation. Sorry, this isn't exactly the same data as the one before, but you get to see what our code outputs, how this runs. This is with the perceptron model, and the good agent being able to profit, the bad agent losing funds, and that accuracy kind of trending towards that ideal value. So here's some gas costs for it. Again, the perceptron usually being the cheapest, naive Bayes also being pretty close here. And deployment cost, again, being high for these ones, these two, because they need to have essentially double the data as this sparse perceptron. Okay, so kind of to sum that all up, the perceptron is usually cheaper to use because it's smaller. It's not storing as much information for all the multiple classes. The models, all of them are expensive to deploy, like you saw. Depends who you are. This 46 US dollars might be kind of expensive, but that's a one-time cost that basically the developer or company deploying this model has to pay, which they would have to pay anyway if they were using a more classical cloud system like Azure, Amazon, Google Cloud, or so on. Most of the models can maintain their accuracy despite malicious attempts, so that's what's important here, because a big concern could be, well, why would I put my model on a blockchain and leave it open to update if people can be malicious? But I'm showing that the models can still maintain their accuracy and the good people can profit. But what's important is that users need to be able to monitor that accuracy somehow. So there needs to be people, hopefully several groups, publishing accuracies on their hidden test sets and encouraging people to build their own test sets. Just like you might use some other API, you're going to have some of your own, at least, integration test cases to make sure it works as expected. And even if a model is corrupted, it's not such a big deal because it's all in a smart contract on a blockchain, and you can just kind of fork from an earlier version when you believe that the model was performing well. So kind of the bigger overall vision here is that maybe one day companies can share models just like how they share open source code right now. And it doesn't mean they would just share the model, they can still build their own layers on top of that, just like how companies might use similar APIs in open source code now and piece them together. That would be amazing if people can do it with machine learning models right now. So some of the next steps are to analyze more incentive mechanisms. I was mainly talking about our self-assessment one, but there's other incentive mechanisms that we've talked about before. Figuring out good models to use. I've kind of skipped over talking about privacy. We should be able to handle private data. That would be a great goal for the system, and so on. There's a few FAQ comments people usually ask. I've answered most of these on this link, which is actually on our GitHub README. So thank you.